What specific factors permitted the Earth to endure when an infinite number of other environments could not survive? The vast majority of alternative worlds collapsed right at the initial phase of their creation. They were completely wiped out by devastating environments and unyielding interplanetary gales. When viewed from the depths of space, our Earth presents itself as a stunning, cryptic blue sphere, yet underneath that magnificent visual exterior exists an incredibly delicate and insecure physical truth. The Earth initiated its development roughly 4.5 billion years in the past. It slowly came into existence out of swirling masses of interstellar gas and space dust inside a specific zone of the Milky Way galaxy. Starting from a violent Earth-shattering impact with a rogue world named Theia, all the way to the creation of a spinning, liquid ion center that produces a protective cosmic magnetic shield, every single step completely determined its ultimate destiny. It happened to settle directly inside the circumstellar habitable zone, a privileged region where the surrounding temperatures are perfectly balanced for liquid water to gather on a surface. According to the calculations of researchers, approximately 70% of our planet's exterior is currently submerged under massive oceans. These precise elements, alongside a multitude of alternative essential circumstances, forged an absolutely unparalleled planetary body. It became a solitary place where biological organisms could step forward and steadily change over the course of countless millennia. Right now, we are embarking on an epic exploration to discover one of the most resilient cosmic survivors in the history of the universe. This is the complete chronicle of the dramatic dawn of planet Earth. Going back roughly 6 billion years ago, the place we call Earth was absolutely nothing more than an immense spread-out molecular cloud drifting in the void. It was completely freezing, utterly pitch black, completely scattered, and floated aimlessly through the deep emptiness of interstellar space. Contained within this vast expanse was a raw blend of fundamental hydrogen, basic helium, and much weightier elemental blocks like carbon, silicon, iron, and oxygen, which were the ancient remnants left behind by cataclysmic supernova explosions from previous iterations of stars that had blossomed and burned out long before. For a massive stretch of time, this gargantuan cloud lingered in a highly unstable equilibrium between structural harmony and total gravitational ruin. The internal thermal energy pushed outward against the crushing pull of gravity. Eventually, a minor disruption, which might have been a violent shockwave rippling from a nearby dying star's explosion, proved to be completely sufficient to break that delicate state of balance. The moment the overall density of the accumulated matter pushed past the critical threshold known as Jean's instability. The force of gravity started to take complete control, causing the entire cloud to shrink and crash violently inward on itself. At the absolute focal point of this imploding collection of mass, the raw matter was squeezed together so intensely that thermonuclear fusion processes suddenly ignited, and our parent sun was officially born. However, the creation of the sun was by no means a final conclusion to the story. Rather, it was the opening chapter of a vastly more unforgiving and chaotic environment. Not all of the remaining interstellar dust and gas dropped directly into the newborn central star. Instead, the leftover material hurled itself outward, flattening into a highly condensed, rapidly spinning circumstellar protoplanetary disk. This immense disk was a highly volatile and lawless territory where swirling torrents of gas, crashing pieces of space rock, and perpetually warped orbital paths completely defined its underlying character. Inside this turbulent protoplanetary disk, development did not proceed according to any organic or biological pathways, but rather obeyed the unyielding, violent laws of pure physics. Tiny micron-sized specks of cosmic dust slammed into each other and clung together entirely through basic electrostatic forces. They steadily expanded into slightly larger clusters, which then transformed into distinct grains and eventually developed into small pebbles. The moment these fragments achieved a large enough physical proportions, their own internal gravitational pull started to exert a genuine influence on their surroundings. Following that critical milestone, the overall mechanism of material accretion dramatically surged forward, assembling kilometre-scale massive rocky blocks that astronomers refer to as planetesimals. These primitive bodies steadily pulled in all the scattered material in their immediate paths, violently crashing into one another in high-energy impacts of unfathomable power. From the remnants of these planetesimals, slightly larger planetary embryos gradually came forward, but the proto-Earth was absolutely nothing special during this primitive stage of development. It existed as merely one solitary embryo out of hundreds of identical candidates, all fighting for survival in the interior zone of the nascent solar system. Every single one of these embryos was a potential world, yet the overwhelming majority of them completely collapsed. A number of them were aggressively consumed by much larger competing embryos. Alternative worlds were violently hurled completely out of the developing solar system due to extreme gravitational interactions with their neighbours. Still other bodies were utterly obliterated in catastrophic impacts that generated enough thermal energy to entirely liquefy their outer crusts. Throughout this hazardous developmental epoch, the proto-Earth managed to endure only on a temporary, highly uncertain basis. Every single incoming space collision stood as both a fatal threat of total eradication and an active path for expanding its mass. Each descending piece of rock possessed the capability to either make the Earth physically grander or completely wipe its existence off the cosmic map. The exterior of the world was not a solid landscape, but rather a roiling global ocean of liquid magma where the internal temperatures soared so high that molten metals and heavy silicates naturally split apart into distinct geological layers. To fully grasp the reasons why our Earth was offered this exceptionally rare and fragile opportunity for survival, we must direct our attention toward the outer solar system and look at Jupiter. This gas giant is the colossal entity that quietly dictated the ultimate destiny of every single world in the solar system. Quite unlike the slow development of Earth or Mars, contemporary scientific models of planetary creation, which merge our computer simulations with direct telescope observations of active protoplanetary disks surrounding distant infant stars, reveal that Jupiter materialized incredibly early in the solar system's history, arriving a mere 1 to 3 million years after the Sun first ignited. While the vast majority of the matter inside the solar disk still existed in the form of raw hydrogen and helium gas, Jupiter had already successfully constructed an incredibly dense, solid planet core with a calculated mass somewhere between 10 and 20 times the entire weight of modern Earth. The very moment this primitive core expanded to a specific critical scale, an unstoppable phase of runaway gas accumulation instantly triggered. Jupiter aggressively pulled in the nearby hydrogen and helium gas at an ever-multiplying pace, rapidly transforming into a gargantuan gas giant with a concluding mass exceeding 300 times that of the Earth. The immense gravitational reach of Jupiter does a great deal more than merely keep its large family of moons trapped in stable orbits. It completely commands and dictates the entire physical and orbital layout of the surrounding planetary disk. It warps orbital trajectories, aggressively churns up raw materials, and completely reshapes the long-term developmental history of every single alternative world. When we look out into deep space and monitor solar systems far past our own cosmic neighbourhood, a deeply disturbing and consistent trend begins to reveal itself. In every single region where massive gas giants take shape early in their histories and subsequently migrate inward toward their stars, super-Earths routinely manifest. These are massive rocky worlds, several times more heavy than the Earth that orbit incredibly close to their parent stars, remaining scorched, intensely pressurized, and completely uninhabitable to any biological life forms as we understand them. According to the specialized Grand Tack hypothesis, which scientists built by analyzing detailed orbital models alongside the current mass layout of our inner terrestrial worlds, Jupiter absolutely did not stay at its original birth coordinates after its initial creation, Violent physical friction and interactions between Jupiter and the surrounding thick gas disk produced powerful gravitational torques that forced the giant planet to spiral inward toward the Sun. It potentially migrated all the way into a region around 1.5 astronomical units away from the Sun, which is a spatial zone located extremely close to where Mars orbits in the modern day. Throughout this disruptive celestial journey, Jupiter operated exactly like a monstrous gravitational blender, completely scattering and physically evicting raw planet-building materials straight out of the inner solar system. Under normal circumstances, a gas giant sweeping deep into the internal zones of a solar system delivers an absolute death warrant for any developing rocky worlds. However, the architecture of the cosmos does not always execute simple, predictable screenplays. Just as this was occurring, Saturn managed to take shape further out, and the moment it collected a large enough physical mass, it began to exert a powerful gravitational pull on Jupiter. The two colossal worlds eventually locked into a specific orbital resonance, which represents a physically stable yet immensely impactful structural arrangement. The specific title of Grand Tack, which astronomers lifted straight from classic sailing ship terminology, perfectly mirrors a sharp steering maneuver that fundamentally transformed the layout of the entire solar system. Due to this event, the internal zone of the solar system was heavily drained of its raw materials, which permanently blocked the developing rocky planetary embryos from growing to an oversized state. The external zone of the solar system, by complete contrast, stayed highly concentrated with thick gases and frozen ice, which permitted the gas giants to go right on expanding. The final outcome of this cosmic sailing maneuver was a sharply segregated and organized solar system featuring tiny rocky worlds nestled in the inner tracks and massive gas giants holding the outer lanes. It was precisely this dramatic shortage of leftover rocky material that completely obstructed the development of hostile super-Earths inside our inner solar neighbourhood. This is an environmental outcome that stands as exceptionally rare when contrasted against the broad data collected from deep space exoplanetary surveys. Therefore, the Earth is the direct byproduct of a cosmic neighbourhood that was deeply warped and rearranged by extreme planetary movements. In popular science, Jupiter is frequently portrayed as an invaluable gravitational defender that preserves Earth by blocking descending asteroids. However, during this raw, primitive era, it behaved as anything but a benevolent protector. It severely disrupted the normal course of planet building and systematically wiped out a vast number of potential planetary choices. It ultimately left behind merely a handful of small, stable worlds that were tiny enough and structurally sound enough to maintain their ongoing existence. Yet, by completely altering the orbital paths of the few surviving planetary embryos, Jupiter indirectly multiplied the long-term probability of massive, late-stage space collisions. These final monumental impacts completely forged the Earth's distinct physical attributes. Among these violent encounters was one specific collision that did not merely change the surface landscape, but entirely revolutionized our world's long-term atmospheric future, its specific axial lean, and its steady orbital consistency for billions of years into the future. This was the defining crossroad, where the Earth stopped behaving simply as an isolated surviving planet and finally started to transform into a unified, balanced system. It did not occur because of a gentle drop in surface temperatures, nor did it happen due to the sudden manifestation of watery oceans, or an early atmosphere rather. It was caused by an interpersonal collision of catastrophic proportions. This was a space impact so violently intense that it thoroughly overhauled the Earth from its innermost centre all the way to its outer orbital path. Yet, it was simultaneously configured with enough precision that it managed not to blast our world completely out of existence. Out of the immense ruins of that single event, the Moon was officially born, sometime around 4.51 to 4. 47 billion years ago, our planet officially stepped into the Hadean Eon, which was a geological period when the Earth shared absolutely no visual similarities with the hospitable world we live on today. The outer surface was completely devoid of solid land, existing instead as a boiling planet-wide ocean of glowing magma that was perpetually churning, forming temporary crusts, and instantly melting back down. During this extreme epoch, the planet's intense heat was generated by three primary power sources: the leftover kinetic energy trapped from initial planet formation, the intense radioactive breakdown of heavy elements like uranium and thorium, and a persistently high rate of descending space impacts. It was right inside this hyperviolent setting that an independent planet moved on a direct collision course toward us, which researchers have named Theia. Detailed computer models and chemical tracking point to the fact that Theia was roughly equal in scale to the planet Mars, possessing a physical mass equivalent to about 0.1 times the weight of Earth. It was by no means a drifting asteroid or a minor stray rock, but rather a legitimate, fully grown planetary embryo that had developed right alongside the Earth during the final stages of inner solar system growth. Theia did not slam directly into the Earth in a straight head-on crash. Instead, advanced planetary models strongly indicate a glancing. A bleak strike that occurred at a highly shallow tilted angle with an estimated impact velocity of roughly 9 to 11 kilometers per second. The essential component to understanding this event involves how the planetary matter separated right after the crash. The vast majority of Theia's highly dense iron core plunged straight through the impact site, sinking through the interior to permanently merge with the Earth's own central core. This process greatly expanded the overall scale, density, and weight of the Earth's metal center. Simultaneously, the considerably lighter, silicate abundant material located in the outer mantles of both Earth and Theia was violently blasted out into the surrounding void of space. This sprayed material quickly settled into a massive, glowing disk of melted debris that circled the damaged Earth. This was by no means an unorganized or chaotic scattering, but rather the unyielding, mathematically certain consequence of impact physics and the fundamental density variations present within planetary ingredients. Out of this massive ring of circling debris, over a time span that required only a few thousand to a few tens of thousand years, the scattered pieces started to clump back together under the steady pull of their own internal gravity. Contemporary models confirm that the Moon consolidated in an extraordinarily brief period when measured against the grand scale of geological time. Authentic lunar rock samples that were gathered and brought back by the historic Apollo space missions demonstrate oxygen isotope signatures that are virtually indistinguishable from the rocks found on Earth, falling well within standard baseline errors. Throughout our solar system, every single celestial body normally exhibits highly individualized isotopic signatures, which mirror the specific location and environmental conditions under which it originally grew. This nearly flawless isotopic match between our two worlds strongly proves that the Earth and the Moon originally drew their ingredients from the exact same primary cosmic reservoir. This is a critical point that all alternative theories of moon formation struggle to clarify in a believable way. Furthermore, this ancient cosmic collision accomplished far more than just hanging the Moon in the evening sky. It fundamentally overhauled the physical spin of our planet. Right after the crash, the Earth spun at a vastly higher speed than it does in the modern world. Scientific calculations indicate that a complete day-night cycle during that era might have lasted a mere 4 to 6 hours. Over the passing millennia, powerful gravitational tidal friction between the Earth and the newly formed Moon slowly dragged down the speed of the Earth's rotation, while simultaneously nudging the Moon outward. This slow outward drift persists to this day at a measured pace of roughly 3.8 centimeters every single year. This long-term spatial transformation was not just an irrelevant mechanical detail, it directly commanded future planetary weather patterns and established the fundamental biological cycles of life. Most critical of all these outcomes was the permanent anchoring of the Earth's specific axial tilt. The spin axis of the Earth is currently canted at an angle of roughly 23.5 degrees, which directly gives rise to our annual change of seasons. Comprehensive, long-term computer simulations firmly demonstrate that if we did not possess our Moon, the Earth's precise axial tilt would fluctuate erratically and wildly due to the combined gravitational tugging of the other planets in the solar system. It would swing unpredictably by tens of degrees over relatively brief stretches of time. The Moon, carrying a physical mass that is equivalent to exactly 181 of the Earth's weight, operates as an invaluable gravitational anchor. It has successfully pinned the Earth's axial lean within an exceptionally tight, secure window for billions of consecutive years. Consequently, the very same cataclysmic disaster that possessed enough raw energy to thoroughly wipe out every single bit of the planet's original surface structures ultimately transformed into the primary prerequisite for securing its long-term environmental balance. Biological life on Earth did not emerge from a quiet, peaceful history. Instead, it is the direct byproduct of a monumental cosmic accident that was perfectly steered by the mathematical rules of probability. Following the immense collisions that definitively forged the Earth's physical shape, its tilt and its motion, the planet entered a much more quiet, yet equally demanding trial, finding a way to permanently grip its atmosphere and liquid water. Earth's abundance of water did not originate from one isolated celestial event. Detailed calculations of the specific deuterium to hydrogen isotope ratios found within our global ocean waters demonstrate a striking, undeniable chemical resemblance to highly volatile, carbon-rich carbonaceous chondrite meteorites. This matching chemical thumbprint strongly suggests that a considerable percentage of our world's primary liquid water inventory was actively transported and delivered directly from the freezing outer sectors of the solar system. This water delivery occurred over millions of years, heavily accelerating during the intense, chaotic epoch known as the Late Heavy Bombardment. These primitive carbonaceous meteorites carried significant amounts of pure water trapped securely in the structural form of frozen ice and chemically bonded, hydrated mineral structures. The very moment these rocky bodies hurtled downward and violently crashed onto the surface of the young, developing Earth, they directly deposited their icy payloads, systematically adding to and expanding the planet's primary surface water reserves. Yet, comprehensive geochemical datasets also point directly to an alternative internal water source, one that was far quieter, more persistent, and deeply integrated into the planet's structure: endogenous water. Deep within the massive, hidden expanses of the Earth's interior mantle, water can be safely locked away at the molecular scale, held tightly in the form of reactive hydroxyl groups inside the crystalline structures of deep-seated silicate minerals. During the first few 100 million years of the solar system's existence, the infant sun was an incredibly unstable and violent host, routinely emitting destructive ultraviolet and high-energy X-ray radiation that was calculated to be anywhere from 2 to 5 times more intense than what we observe in the modern era. This fierce radiation was accompanied by a relentless, highly concentrated solar wind consisting of fast-moving, charged stellar particles. These severe space weather processes possessed the absolute capability to strip away a developing planet's volatile atmosphere layer by layer through relentless kinetic erosion and high-energy atmospheric escape. This erosion is particularly effective at removing lighter, low-mass gaseous elements like hydrogen from the upper reaches of a world. We can clearly see the tragic consequences of this process by observing our neighbour Mars, which grew to possess only about 10% of the total physical mass of Earth. Because of its significantly smaller scale, Mars cooled down at a much faster rate, causing its churning metallic core to solidify entirely early in its history. This early solidification caused its protective, global magnetic field to completely shut down and disappear within the first few 100 million years of its formation. Devoid of a protective magnetosphere shield, the planet's upper atmosphere was left entirely vulnerable, allowing the unmitigated solar wind to directly erode, scrape away, and deplete the Martian air. Sophisticated orbital data gathered by modern space probes firmly prove that Mars once boasted abundant liquid water flowing across its surface, complete with active rivers, deep valleys, and wide lake basins. However, as the protective Martian atmosphere was systematically thinned out and the surrounding atmospheric pressure dropped past a critical point, surface liquid water became completely unstable. It was rapidly forced to either evaporate completely or freeze solid, ultimately being lost to the vacuum of space forever. Mars did not ultimately fail as a habitable candidate because it lacked water during its initial formation. It failed simply because its small size and lack of a core dynamo meant it could not hold on to that water over long stretches of time. The early survival of Earth hinged entirely on two major factors. First, it required a large enough physical mass to exert a strong gravitational pull, ensuring it could successfully retain a thick envelope of atmospheric gases over vast expanses of deep time. Second was the remarkably early creation of a robust global magnetic field. Detailed paleomagnetic studies analysing incredibly resilient, ancient zircon mineral crystals strongly suggest that the Earth may have successfully generated an active, fully functional magnetic field as early as 4.2 billion years ago. This ancient magnetic field produced a wide, protective magnetosphere that successfully deflected the vast majority of the incoming solar wind. It dramatically minimised atmospheric erosion and effectively stopped the runaway loss of lighter gases like hydrogen, which is the foundational chemical building block required for retaining liquid water. At a much deeper system level, the profound physical coupling established between the early global oceans and the overlying atmosphere produced an immense thermal inertia. This massive thermal buffer drastically reduced the overall scale and severity of global climate fluctuations. Liquid water is remarkably efficient at absorbing, storing, and redistributing thermal energy on a global scale. At the same time, the global atmosphere actively transports excess heat away from the scorched equator and pushes it toward the freezing higher latitudes. A planetary body that successfully maintains a stable balance of liquid water and atmospheric gases does vastly more than just survive. It essentially functions as a system with a long-term memory, steadily accumulating and building upon past physical states over time, rather than being wiped completely clean after every random cosmic catastrophe. When Earth successfully retained its liquid water and thick atmosphere, it preserved far more than just raw material. It locked in a profound future potential, the potential for basic chemistry to steadily grow more complex. It allowed physical energy to be distributed slowly and predictably through moving oceans and circulating air. It created an environment where chemical reactions could persist uninterrupted for long enough periods to allow entirely new, highly organised material structures to steadily emerge from the chaos. A planet that holds onto its water is a world gifted with a long, continuous history where the past can steadily layer upon itself instead of being erased. Yet the retention of water and an atmosphere merely set the physical stage. Once that environmental stage was securely established and managed to endure for long enough, a far deeper, more revolutionary phase transition occurred. Ordinary matter began to store information. Out of the deep, dark oceans and the highly concentrated chemical energy sources found on the ocean floor, early life successfully emerged. Following this event, Earth entered a brand new developmental phase in which it no longer operated solely under the unyielding laws of physics and basic chemistry. Instead, the planet began to actively record, remember, and adapt to its own history. This phase marked the dawn of biological life and the very first time our planet gained a true physical memory. When Earth successfully maintained its water and atmosphere across millions of years, an invisible evolutionary threshold was crossed. There was no massive cosmic explosion, nor was there any brilliant change instantly visible from the depths of space. Yet, from that precise historical moment onward, our world would never be the same. The ancient geological record preserves subtle, yet unmistakable traces of this early transition. Extremely old rocks found in Greenland and Western Australia which have been accurately dated by scientists to around 3.8 to 3.7 billion years ago, demonstrate a clear, distinct chemical preference for the lighter carbon-12 isotope over the heavier carbon-13 isotope. This specific isotope imbalance stands as a classic, distinctive signature left behind by biological processes, proving that life had already taken a firm hold on our world. This primitive life did not begin its journey up on the harsh, unforgiving surface of the land. Up there, destructive solar ultraviolet radiation still rained down completely unmitigated, and small space impacts continued to routinely plague the landscape. Instead, a growing mountain of scientific evidence and detailed biological models point directly to the deep ocean as life's true cradle. Life likely began around deep hydrothermal vents scattered along the volcanic ocean floor. At these extreme locations, near freezing, high-pressure seawater directly encountered superheated rock rising up from the planet's mantle, creating immense thermal and chemical gradients. These powerful energy gradients, rather than raw sunlight, provided a highly stable, continuous energy source capable of powering early prebiotic chemical reactions. These ancient hydrothermal vents were incredibly rich in vital dissolved gases and elements, including hydrogen, methane, hydrogen sulfide, and transition metals like iron and nickel. These abundant chemical components enabled simple reduction-oxidation reactions to occur spontaneously, generating a steady, non-stop supply of usable chemical energy. Within these protected, mineral-rich microenvironments, organic molecules were able to safely accumulate, combine into complex chains, and begin replicating in rudimentary ways. This early life did not require highly complex strands of DNA or fully formed modern cellular walls to exist. It needed only one fundamental capability: the capacity to maintain a stable internal structure in the direct face of surrounding environmental chaos. The Earth's atmosphere during this early epoch was completely different from the air we breathe today. It was an anoxic, reducing atmosphere composed predominantly of nitrogen, carbon dioxide, water vapor, and methane. Completely devoid of free oxygen gas. Over hundreds of millions of years, these simple biological systems quietly experimented with countless alternative ways of exchanging and managing chemical energy. One of the most radical, earth-shattering innovations ever achieved by these organisms was the development of photosynthesis. In its earliest evolutionary iterations, photosynthesis did not actually produce any oxygen as a byproduct. Instead, it utilized alternative, readily available compounds such as dissolved sulfides or iron molecules to act as essential electron donors. Then, around 7 billion years ago, a truly revolutionary lineage of microorganisms known as cyanobacteria successfully developed the biological capability to split ordinary water molecules apart to use as an abundant electron source. The immediate byproduct of this new water-splitting chemical reaction was free molecular oxygen. This sudden release of a highly reactive gas was initially a massive planetary disaster. Free oxygen was highly toxic to the vast majority of the existing anaerobic organisms, and much of the planet's existing primitive biosphere was completely wiped out in a mass extinction event. However, this great oxidation event simultaneously served as the ultimate turning point that opened up a magnificent new era for life. The resilient organisms that managed to survive this crisis were those that successfully evolved to tolerate the presence of oxygen and eventually to aggressively exploit it through the process of aerobic respiration. Aerobic respiration is an incredibly efficient metabolic process capable of producing far more usable cellular energy than old anaerobic pathways. The slow, steady accumulation of free oxygen gas within the atmosphere eventually led to the creation of a high-altitude ozone layer. This ozone shield dramatically reduced the amount of destructive ultraviolet radiation reaching the planet's surface, opening up an entirely new path for life to migrate out of the deep ocean, move into shallower coastal waters, and eventually conquer the dry land. As the biosphere expanded, the global oceans actively absorbed immense amounts of carbon dioxide, working in tandem with the atmosphere to regulate global temperatures. The planetary carbon cycle became profoundly linked with biological activity, acting as a natural thermostat that prevented the Earth from experiencing permanent runaway freezing or boiling cycles. This deep interconnection transformed the planet into an integrated, self-regulating system. Throughout its long journey, this system would endure severe environmental crises, massive extinctions, and dramatic cycles of planetary collapse and reorganization. Yet, because it possessed the ability to retain its core ingredients and build upon its past successes, it maintained an unbroken thread of continuity. This continuity provided the planet with the unique capacity to steadily evolve over billions of years, rather than being reset completely back to zero after every random external catastrophe. The birth of Earth was absolutely not a brief random stroke of luck, but the direct consequence of a persistent, highly organised process of construction spanning hundreds of millions of years. Emerging from a chaotic, lawless disk of space debris orbiting a young sun, the gradual systematic accumulation of matter from microscopic dust grains all the way up to planet-shattering collisions ultimately forged an extraordinarily complex geological and biological body. The continuous evolutionary progress of this planet did not occur without severe environmental interruptions and structural crises. Throughout its immense historical timeline, Earth was repeatedly subjected to devastating global events, widespread biological mass extinctions, and severe cycles of systemic collapse followed by radical systemic reorganization. Yet, despite the sheer violence of these planetary disruptions, the deeply integrated nature of the world created a resilient framework of continuous development, granting our planet the unique capacity to steadily evolve over billions of years. Rather than being completely reset to a completely lifeless state of zero after every random external catastrophe or internal volcanic upheaval. The Earth preserved its core historical foundation. The birth and long-term stabilization of planet Earth was absolutely not a brief, random, or instantaneous event. Instead, it stood as the definitive result of an exceptionally long, meticulous, and persistent process of physical construction spanning across hundreds of millions of consecutive years. Emerging slowly out of the chaotic, lawless protoplanetary disk of swirling matter surrounding our infant parent Sun, the planet's primary architecture was established piece by piece. The gradual, relentless accumulation of matter, advancing systematically from microscopic dust grains sticking together all the way to catastrophic, high-energy collisions between massive planetesimals, forged an incredibly complex and dynamic geological body. At the very deepest heart of this swirling planetary chaos, a profound process of structural differentiation unfolded with remarkable chemical and physical precision. A roiling, molten metallic core composed primarily of liquid iron and nickel steadily formed at the exact centre of the mass. This dense, churning core began generating an invisible, yet incredibly resilient global magnetic shield. This robust magnetosphere effectively wrapped around the entire world, successfully protecting the planet's surface from the highly destructive, erosive forces of incoming cosmic radiation and harsh solar gales, while safely preserving its early, vulnerable atmosphere layer from escaping into the vacuum of space. As the outer layers of the planet slowly began to cool over millions of years, a solid rocky crust eventually formed, sealing in the intense geothermal energy below. Volcanoes erupted non-stop across the young landscape, pumping vast quantities of carbon dioxide, nitrogen, and water vapour back into the sky, constantly replenishing the primitive atmosphere. When the surface temperatures finally dropped below the boiling point of water, a monumental shift occurred. The water vapour in the atmosphere condensed into torrential, unceasing rain. For thousands of years, water poured from the heavens, pooling into the low-lying basins of the crust, and creating the very first global oceans. These oceans were not just passive bodies of water, they acted as a massive global chemical laboratory where complex organic molecules could gather, interact, and organise, without being destroyed by the sun's harsh ultraviolet rays. With the stabilizing presence of the moon pinning the planet's axial tilt, the global climate remained remarkably balanced, allowing these primitive oceans to survive for hundreds of millions of years. This long-term environmental consistency provided the perfect cradle for early life to take root around the mineral-rich hydrothermal vents deep on the ocean floor. As these primitive organisms adapted, they eventually evolved the capacity to perform oxygenic photosynthesis, completely altering the chemical makeup of the entire atmosphere. The resulting accumulation of free oxygen led to the creation of a high-altitude ozone layer, which blocked harmful solar radiation and made it safe for life to move out of the seas and conquer the dry land. This incredible transformation completely shifted the Earth from a system ruled entirely by basic physics and raw chemistry into a living world. Every single layer of the planet, from the churning liquid iron dynamo deep in the core, to the shifting tectonic plates of the rocky mantle, to the moving currents of the global oceans and the protective gases of the atmosphere, became deeply interconnected with the active biosphere. This powerful, self-regulating feedback loop allowed the Earth to successfully buffer itself against external threats, ensuring that life could continuously adapt, survive, and thrive through every major geological era. When we look out into the vast, silent stretches of the wider universe, we begin to truly appreciate the incredible rarity of our world's long-term survival. Countless alternative planetary embryos were destroyed, swallowed up, or cast out into the freezing void of deep space before they ever had a chance to develop. Our planet managed to survive a gauntlet of cosmic disasters, perfectly balancing the cold. Mathematical laws of orbital mechanics with the volatile chemistry of a young solar system. It is this long chain of perfectly timed accidents, guided by the unyielding rules of physics, that ultimately established the singular value of this blue planet within the infinite cosmic landscape.